the best.
You're on ends obsessed with that because of like the way that saying that when that happens to people, they start to think of maths in LaTeX, not the way that we do visually and stuff like that.
Yeah, but I think of maths in LaTeX.
Well,
Do you?
Yeah.
I think of integral as an integral, not a /e underscore a.
Yeah.
Do you not notice that even when I'm typing in Slack, I just type it in LaTeX?
Well, yeah, I mean, so do I. Like in a message to a friend, like, hey,
Yeah.
there's like, oh, it's, /frac beta on gamma or something.
But I've got to the point now that if I'm doing a proof, I do it directly in LaTeX. I very rarely write it up separately.
So you think if we blindfolded you and you had to listen to the LaTeX, you do it?
Not
Reasonably well.
My biggest problem is I can't type very well. That's it.
Because the classy thing I used to do a lot is I cycle to and from work, and as I'm cycling, in my mind I go, right, here's the whiteboard, and I start putting various bits of mathematics so I can see not completely, but enough that I can start manipulating and going, I can see the patterns.
On your bike.
Yeah.
Well, he lives like nice and flat area. It's not very strenuous.
Yeah. The worst thing is, every so often I have this mind image and I've got it all right, and then Alison will say things like, so should we have such and such for tea? And it just goes, boom. And I give her a look and she goes, what? And I'm like, I just had it right in my head. And she goes, well, there's no sign. It's like, but that's me. So, am I recording? Yes, I am recording. Reminder, you have your presentations on Friday. You know the order, you know what you need to talk about. It will be 4 minutes. It will be exactly 4 minutes. I will be timing you. When the alarm goes off, you stop, you sit down, the next person gets up. We don't have enough time for, but just, can I not? No. 4 minutes is 4 minutes. Simple as that. Don't overthink it. It's short, it's sweet. It's only worth 5%. The idea is you're going to explain your method, and you have the ideas, the goals you're looking for in that handout to domain experts. We will have 4 domain experts. We have Professor Mark Hutchinson, we have Associate Professor Janet Bowen, we have Dr. Bastien Lemaire and Dr. Janet Kohler, who are going to come and be your markers as well as me. Each of them criterion are given in the handout. I will give you a mark between 0 and 5 for each of them sections. We will then look at them and we will rank them and use that as your final score.
Wait, so Gary's not rocking that?
No, it's just going to be them. I just wanted domain experts. I don't want too much pressure for you. You have the criteria you have to do. 4 minutes, that's it. Your marks will go up. That's it. No problem.
Can we use a prepared piece of paper with some example data?
If you want to, yes. Remember, all you have is the whiteboards and that document camera.
Right.
No slides, no stuff like that. If you want to turn up with something prepared, fine. You saw the criteria we had there. I mean, 4 minutes is short, it's sweet. You're worried. You're not sure. Okay. Also, this Wednesday, we're probably going to have a little bit of a workshop in the lecture, so bring along laptops, if you don't already, or iPads, or something you can access the internet with. Cool. So this last lecture, we're going to look at a couple of things, a little bit of pointers. A lot of this is taken from another PDF I put in the notes called Mining Massive Data Sets. So it's about map reduce and hash functions. So it's about some of the techniques you would use when you start dealing with big data. So I'm going to start with an example of what we call a hash function. And a hash function is a very simple thing. It will take a hash key, so a key type value, and we'll talk a lot about this when we do map reduce, and it will return a bucket number. You can think of it as a bin number, but computer science often use bucket instead of bin. And basically it's going to be an integer, normally in the range 0 to b minus 1, where b is the number of buckets. So you give it some sort of key. It could be a string, it could be a number, and it will do some sort of function, and it will just spit out a number between 0 and b minus 1. Okay. And you can use this to speed code up. It's probably the best way of describing it. So I'm going to illustrate this by looking at some basic bioinformatics, so some DNA. So here what we've got is we've got a DNA sequence from the wood mouse. So here you can see that we've got a mixture, a string that has A's, C's, G's, T's, and also N. N just means we don't know what is at the position. It could be an A, C, T, or G. So these are what we call nucleotides. So this is a piece of DNA. And this DNA is very, very long. It can be thousands and thousands to billions of characters long. And a common thing we want to look for is what they call motifs, or k-mers. So you might want to look and say, what are all the strings of length 4? And what are the most common ones? So often when you're looking at DNA, you're interested in these motifs, or k-mers. So let's imagine that we wanted to do that. We just wanted to say, perhaps say, find me the most common substring of length 5 in this DNA fragment. Well, here's an example where I've got all the k-mers. So when you look at that wood mouse, there are 7 substrings that have the structure CT, AAT, etc. So how would you actually do this? You know, how could you actually count the k-mers? Well, let's start with my really bad code. So here's my bad code. So it's nice and easy. I take my DNA and I give it a k-mer, and it basically loops along that k-mer saying, is that k-mer there? And if it is, it just stores it and just adds it by 1. Absolutely fine. Beautiful bit of code. So, and then all I have to do is I have to think about all possible k-mers. So I do it, for example, for A, and then I'll do it for A, and A, and off I go. Beautiful bit of code.
Sounds good to me.
So let's see how long it's going to take. So the number of k-mers, if I have a k-mer, the number of them will be 4 to the k. So obviously if it's 5 k-mers long, so 5 long, it's going to be 4 to the 5. And then every time we check a k-mer, we loop through the DNA, and that will take me n, where n is the length of the DNA, minus k plus 1 steps. So that is my total number of steps. So let's imagine I want to just do the 5 k-mers for the human genome. The human genome is 3 billion base pairs long. So with my really good code, well, here's my calculation. I want to do 5-mers. That's how many I have to steps. We're going to assume that each step takes basically 0.0001 of a second. So the good thing is, if we run that through, my code at the moment is going to take 3.247 years.
Sure, but at least it's linear in the number.
Yeah, that's good.
I've seen worse.
And it will probably stop after 2 years because I made a mistake somewhere, because I know my code. So how can we use hashes to make that better? So imagine I had a simple system that will take, for example, here's a tumor. They're seriously called tumors. What are you laughing at?
Why?
Because it's a 2 and then a mer. So there's tumors. Takes that and it returns an index. Now, I said before it was 0 to b minus 1 because most hash functions are for languages like Python and for C, where your arrays start at position 0. R, remember, when you do a vector, it starts at position 1. So if I can write a function that will take a k-mer and return a number, then it's really easy because every time I get to that k-mer, I basically go to that array at that position and I just add 1 to it. And it's an order 1. You take this function and it tells you where to put that 1 instantly. So let me write here's my beautiful little hash function. So all I did in this case, I actually counted in base 4. So I converted it by counting to base 4, where all my A's get mapped to 0, my C's 1, my G's 2, and my final one mapped to 3. So this function is just converting any string into a number base 4, and hence that's my position to put it in that array. Here's me actually doing it in R, and here's it working. So for example, if I give it A, it returns 1, AC, 2, TG, 15. In fact, the nice thing is, this will do more than my 2-mers. It will do my 3-mers and my 4-mers and my 5-mers. Nice and easy. So here's my function. I ran it on the wood mouse, and it spit out all my number of k-mers for the different ones. Okay. To be honest, just to show you it actually works, this is a standard thing that we do. This package has a count function that does it automatically. So you can see that my hash function works well and matches what they do.
Why is AC and AA both 70? Oh, it's not no curve, sorry, yeah, my bad. I thought it was your mapping.
Sorry. Now I'm actually going to do a hash. So you can actually do hashes. So you've heard these before. They're called a named list in C. They're called a dictionary in Python. I can't remember what they're called in Perl. In R, they're called hashes. So you can actually create a hash. Yeah. So they're a strong structure, and the structure will be such that you can basically have what we call key value pairs. It will underneath take care of all the looking after everything. But basically it has a system that you give it in a key, which will be a string, and it will know exactly where to put that in its hash. Now so far we've assumed that every key maps to one and only one place. That's fine. Occasionally you can get what we call a non-perfect hash, where two keys can be mapped to the same place. So these are where we're assuming that if you know what the position is in the place you're storing it, it relates to one and only one particular key. But just to warn you, you can sometimes, you'll see things talk about, I can't remember the word now. You have a perfect hash where you don't have collusion or collisions, and then you can have collisions in hashes, where two keys will map to the same place. So anyway, you can actually do hashes in R. It's a bit of a hash your hashes. It's not the best thing, it's a bit of a hack. Where you actually create yourself a new environment called a hash. You set up its parent is to empty, and you set the size. So here I've set it to 100, and I set that to an integer. So we've got 100 buckets there. I also made myself a little print hash function, which what that will do is it will grab all your keys just by listing X, and then you can see it's using its own little self-contained list type structure to find things. We very rarely, hashes in R are badly done, and it's a shame because it's the one thing in Python that's brilliant, is dictionaries. So here's my same code. What it does is it goes along my woodmouse DNA. The nice thing is you can notice with that there's a single for loop, so it's just going to be order n. It grabs the substring. It first of all goes and looks at my k-mer hash and says, is that k-mer already there? If it doesn't exist, well, we better set the count to 1. If it does already exist, let's just basically increase or increment that count by 1. And notice the way I'm doing it is it's very similar if you've seen dictionaries. You've got your hash object, and your key is actually put in the double square brackets. So it does exactly the same thing, and when I print it out, you get the same stuff. The nice thing with mine is mine was a bit cleverer because before with the original one, I hadn't taken into account n, so the n's just couldn't get mapped at all. When I now use hashes in R, it has no problem with them. As far as it's concerned, as long as your structure was large enough, and we only needed, 5 squares, so 25 places, and I got 100, it can do the hash quite nicely. So, honestly though, if you need to do this sort of problem where you need hashes, go and write it in Python. Go and search dictionaries in Python and use them to do it. They are so much better than R. That's where R falls down. So, the reason we started with hash function, you've got this idea that you can take a key, and that will be given an allocated space in memory, and you can then put values in that. So you've got this key value pair structure. So we're now going to use that to do map reduce, which is one way to actually deal with really big data sets. So we're going to talk about how data is stored on big server computers. So what we've got here is an illustration of a big server. And what you've got is you have racks. So these are racks of computers, and within them they will have their individual computer, so drive, which we'll call a node. And then you've got a switch that will control and move stuff between. So this is a very make-believe version of computer storage. And the problem is nodes will every so often decide that this world is not for them and just die. In fact, sometimes whole racks will go, oh, let's go. And so what you need to do is you need to think of having a system, so if your data is on a single node, or your process, your calculation is being done on a single node, you're not going to lose everything. You need to build in some sort of replication type system, so your data is split in numerous places, and if a node goes down or a rack goes down, you can still either keep doing your calculation or still get your data. So the idea was to have a distributed file structure. So we need to get rid of, basically take into account that if we have a loss of a single node or a loss of an entire rack, we don't lose all our data or all our calculations we were doing at that point on our data. So the idea of a distributed file structure is that all our files will be stored redundantly. So you will have every copy of data will be usually have replication k times, and it will be hopefully not in all the same node, it will be moved elsewhere. And so if you're going to start doing that, if you're going to take your data and have 3 versions of it, say, split over a couple of racks, you need to have a system that basically knows where everything is kept. So your distributed file structure that you see in these things basically takes your data, and what it does is it splits it into chunks. Your data is the value, and where it is now the key. So you've got this key value pair of distributing your data amongst various places. So files are divided into chunks, typically about 64 megabytes. Each chunk is replicated. So for example, 3 times at 3 different nodes, and the master node gives the location of the chunks. So basically you take your data, you split it up, you put it in all those various places, and you have a master file, and that's also usually replicated as well, because your data is your master file, because it uses everything that says, right, there's a copy of the first chunk here, here, and here, and then if anything goes down, it doesn't matter, you've still got 2 copies. There's a lot of technical details about things like data just keeps saying things like, I'm here, I'm here, I'm here, and the master's listening out, and if it doesn't hear it, it knows it should make a new copy quickly because something's gone down and stuff like that. But I'm not going to go into the details. So finally, we're going to get to MapReduce. So MapReduce is a general concept introduced by Google to take large algorithmic problems and simplify them. And it works on a very simple principle. First of all, you've got your chunks, which remember are these little bits of data split into different files. And then we'll go through a map task. And the map task takes a chunk and it spits out a key value pair. So we'll go, here's a key and here's an associated value. Those are then collected in that group by key section where they grab them together and they put all the key value pairs with the same key together. And then there will be basically a reduced task, and what reduced task we'll see. So now you see you've got each of these chunks going a k, which is your key and your value. And then they've been grouped together, so now for each key you might have a list of values. And then they will go into a reduced task, and that reduced task will take that list of values and do some sort of function of them and put them together and combine it. So let's look at an example. So, just to recap, maps are given one or more chunks which are turned into key value pairs. Key value pairs are collected by the master controller and sorted by keys. Keys are divided among reduced tasks. Said keys go to the same reducer. A reduced task work on one key at a time and combine the values. And the idea is it's basically a divide and conquer. You've got a problem that's going to take lots and lots of stuff, but you can split it. So the classic would be, imagine we had to add up 1,000 numbers. John on do not zone is going to take for ages. If I give you the first 100 numbers, you the next 100, you the next 100, you the next 100, you're now my map stuff. You're going to spit back and go, right, the key was the first 100 numbers and their value was this. You do the same, the same, the same. We can then just add up them final results. We've now reduced the time it takes. That's MapReduce. So here's the example. Please don't tell Matt Rowan this example. He gave me an hour explaining why I was wrong with this example. This is a standard example in the book. I know you can do it cleverer. I know, Matt Rowan, you're better than this. But fuck, it's in the book. Anyway. So, let's assume I want to count words in a repository of documents. So first of all, the input file is going to be an individual document. That's my chunk. And then my map is going to take a document at a time, and it's just going to go through, and every time it sees a word, it spits out, the key is going to be that word, and the value is just going to be the value 1. So it gets the first word, and it goes, right, once, and it spits out once, comma 1. And it gets the next one, upon, and it spits out upon, comma 1. Where your WI is your key, it's just a word. So that's just order, it goes straight down, it just spits a load of these out. Then these just get grabbed together. So it goes, when it goes into your group by, and it goes, right, how many onces were there? And all the onces get grouped together because you can sort by your keys quite easily. There's very fast sort routines. So you just sort them and then you just go down that list and go, right, I've got all my onces. And then your reduce just takes that list of 1, 1, 1, 1, 1, which will be length, however many times there was a once, and just return the length. And now you get your document, which is your key, and how often it appeared. Make sense? Now, of course, as Matt pointed out, gain and fucking gain and fucking gain. Your map could be faster. Your map could actually do that automatic counting at the first time and just spit out once and say, in this document, once was 20 times. But that's a standard example of map reduce in all the textbooks. So, I will show you how you do it. So, this is assuming this works. Did this work? Ooh, it did. Thank goodness for that. Because once you start doing hashes, you have to accept that your world will get harder. So, there's actually a DSL, which will let me do a distributed system list in R. So what I've got is, I've set up a DS storage system. I'm going to use the LFS, there's different types. And I'm going to basically have my data in Hound DFS. And I set up my chunk size to be 50 megabytes. And that was the standard way you do it according to the DS storage command. So then the next thing I did is I said, go into my data Hound Baskerville and have a look. And in there I had 2 text files, which is the first chapter of the Hound of the Baskervilles by Conan Doyle, and the second chapter of the Hound of the Baskervilles. So it's got these, and it's looked in this folder, and I said, there's my data. So I've got my data folder, and what it does, first of all, it looks at it and says, right, I've got it. I know it's there. So that's what it's done. It's said, I've got a DS list, the storage is going to DS, I've told it where the data is. And at the moment, it's actually just returned 2 things, 2 key value pairs, where the first one, it's got basically the C1.text, and information within that, the value is just where it is on my system. Next thing I do is I now write a function that's going to read those in. So this goes, you've got a key pair. So you've got the key, which is the first text document, and the value is just where it is. This now says, with a little try and catch, go and grab the data, read it in. And what I want you to do now is I want you to spit it out, so you've got your key value pair. So the key will be the name of the file, and your value will be all the text within that file. But if you go with this on your system, you'll find that what happens when you look in that folder, there's lots and lots and lots and lots and lots of files appear. Because it's taken them 2 text files, grab them in, and chunk them. So the first chapter, it will go, right, the first chunk, I call it chunk 1, here's some text. Second chunk, chunk 2, here's some text. So it actually distributed it. Now, because it's on my local computer, it's distributed all in one big folder. But if I was on, say, Amazon Cloud Services, it can just distribute it anywhere within your file structure. And it's just keeping a link that says, the first chunk goes here, the second chunk goes here, the third chunk goes here, etc. So now my data is in a distributed file structure in our particular thing, when you run this at home and have a go, you'll find that your folder is just full of all these little folders. And if I have a look at it, for example, I look at the first one and have a look at the first 10 lines, it spits out the first line of chapter 1 of The Hound of the Baskervilles. I assume, without saying you've all read The Hound of the Baskervilles.
No, I've read on the Sherlock Holmes.
Good. You've already got one extra mark. Anyone else want to go for another extra mark in the exam?
What's a book?
What? Yeah, it's really complicated. It's like we used to hate trees, so we'd chop them down and then we'd tattoo them with ink, and that would be a representation of a movie. Yeah, it's very interesting. It's sort of slower. It's more of a you get to control the plot yourself.
It's kind of like an audiobook, but
Yeah, very like it's a bit like a computer game, but you don't get as much choice.
That's interesting.
Yeah, it's less interesting. And here is the second chapter. So we've now got this distributed file structure. It's taking care of everything in the background. It's taking my data, it's put into chunks, it's kept an eye on where all those chunks are, it's ready to go. So now we set up our map function. What's our map function going to do? It's going to take a key pair. So it's going to take, in our case, a chunk of text. And it's going to grab that text, which is the value. First of all, it's going to get rid of punctuation, which is the first string we place. It's going to get rid of any numbers, which is the second string we place. It's going to convert that to lower. It's then going to split that text by the spaces, and then it's going to unlist. Now, unfortunately, when you do that, you do get a couple of blank things in your list. So I got rid of them with the next line, and then finally I return that. So I say I've got basically a vector of words, and I return that as a list where my key is the word and my value is just 1. So and it will take all my chunks. It's doing it on the background, I don't need to care about. It just grabs a chunk and it just spits out every word as a key with the value 1. So there we are. And there's the results. Here's me looking at my data I've got. So you've got chapter 1, Mr. 1, Sherlock 1, Holmes 1, Mr. 1, Sherlock 1, Holmes 1, who 1, was 1, usually 1, and off it goes. And I can reduce that by just saying, go and grab all the keys that are, for example, Sherlock, and add them all together. So it goes and finds every single, it's doing all in the background, every single key value pair that's kept an eye on, grabs all the ones that had key Sherlock. You've got all these ones, they just add them together and spat it out. And then I had a quick look, because I looked at my results, and I noticed that basically Dr. Watson is a little bit egotistical.
Or Sherlock talking a bit more in the first two chapters.
Well, I mean, this is just a standard book, but for some reason, Watson, in the first 2 chapters of the book, is mentioned 11 times. But, and let's face it, these books are called Sherlock Holmes. It is mentioned only altogether 8 times. I'm suspicious the guy who's meant to be writing the books, Dr. Watson, in the books, might be talking about himself a little bit too much.
Sherlock was just monologuing in the first 2 chapters.
About himself?
No,
Or
Sherlock
not?
was
I don't know. But anyway. Okay, so you can do word counts automatically. You all did your tidy text, it's done automatically. So let's think about how we could do something that's a bit more statistical. So first of all, imagine you want to do matrix vector multiplication. So we've got n by n matrix M and a vector V of length n. So we know that the ith element of x is going to be this calculation here. So I'm going to assume that the matrix can't be read in. We have to chunk the matrix, but we can get the vector all in the memory in one go. There's ways of modifying the map reduce when you can't do that. Well, this is how you do it. This is how you actually do big matrix multiplication using map reduce. First of all, we assume that V is in the memory, and we're going to work on chunks of M. For each matrix element Mij, we're going to return a key value pair where the key is going to be I. So basically your key is which row it's in. And your value is just going to be, you take the element of your matrix, the ij element, and you multiply it by the j element of V. So if you think about it, that MapReduce, all it's doing is doing the inside calculation. It's doing that for each chunk. But your computer goes away and does all of them. It doesn't have any order, it just goes and does every single one. And it's going to return and go, here's your row and here's your value. Then all we have to do now is we find all the keys with the same value and we just add them all up, and that will now give us our ith element. Obviously there's got to be some housekeeping. There's a control that makes sure you don't do the same calculation twice. Basically it sends off a chunk to your processor and says go do this calculation, and if it returns it, fine. If it doesn't return at the same time, it will send the chunk off again and bring it back. So now we're going to do something proper hardcore. We're going to do linear regression. So let's have a go. So, think about standard linear regression. We've got y equals x beta plus e. And we know that if I want to get my estimates of b, my beta hat, I do x transpose x to the minus 1 x transpose y. Assume most of you have done numerical methods. And most of you by now should have known, if Lewis taught you well,
Hashtag never invert.
never invert. You're not going to do that inversion. That inversion is not going to work. But it's going to work, but either not in your lifetime or just give you answers that are wrong. So how do you do it? Well, so just so you know that calculation works, here is a standard linear regression in R. So I'm regressing distance on speed with data equals cars. So there's the coefficients. Remember them numbers, they're going to come back again, again, again. And here's me doing exactly, I've got my y, my x, and I've actually done my inversion. Just to show that that calculation does give you the answers that your linear regression does. So one way you can do it instead is you can do what we call the QR decomposition. So you can take x and you can replace it by two matrices Q and R such that QTQ equals the identity. And in that case, you can now do beta hat equals R to the minus 1 QTY. Still have the inversion, still not quite nice. Nice thing about R is it has a nice structure. It is an upper triangular. So inversion is easier to do, which is good. Why am I being tinged? Yeah. Sorry, it's my dad's birthday today. He's just saying thanks.
Is it one of those things like, thanks son for wishing me happy birthday, if you remembered, or was it actually a genuine thank you for wishing me happy birthday?
Yeah, I wished him, because I get the timing right, because I just know that with my family, as long as I send them a WhatsApp about 12 o'clock saying, hey, happy birthday, they're all in bed. Good thing about the time difference. Yeah. I always keep at least one time difference between you and the in-laws. So just to show that that actually works, here is my QR breakdown, and you can grab the Q and the R. And first of all, I notice that if you multiply these two together, you get the data back to show that. But then I actually do the quick calculation, showing that Q times Q is the identity. And finally, I do and get the same calculations out. So that's your QR. Fine. Let's now map reduce that. So my first thing I'm doing is I'm going to map. So I'm going to take my y and my x and I'm going to split it into m blocks. So I'm taking my y and I split it into a load of blocks, and my x, these dimensions, I just split into blocks. So you just partition it into blocks. Same number of columns as the original x, just less rows. So I thought it's about time you saw some really nice code in R. So here's my R code that does the splitting. You can have a look at that, see if you can work out how it works.
What does double hash do? ID equals row number double hash m.
Oh, modulate.
Sorry.
Mod. So I took the row number, I modded it according to m. So now every row is either going to be 0, 1, 2, 3, 4. I then group it by them, and then I nest that data frame structure. Then, because I need matrices, I grabbed each one of them, and I've selected it out using another map on my nested data frame and returned it to a matrix. I also take my y's and I pull them out separately. So now you can see I have altogether 5 rows, which the key is 1, 2, 3, 4, 0. and that relates to a 10 by 2. So altogether, my data originally was a 50 times 2, and I split it to 5 10 by 2 matrices.
What does the pull function do?
It just grabs it.
So
It just.
why do you use it over select?
Pardon?
Why would you use it over select?
You could use it over select.
You just know.
Yeah, you could just do it over select. I just found the pull seemed to give the mapping of pulling it out. The select kept giving me just the whole vector, and I wanted to say, no, give me the vector of that nested data frame. So it's doing the equivalent to select, but I found it was the only way I could get it to work once I'd actually done the nesting. So here is an illustration that basically there's the first 10 rows of my design and my first 10 elements of my Y. So now I'm going to do my QR decomposition on each of the X matrices separately. So if I'd done it before, I would have had to do I know it's not hard, a 50 by 2 QR. Trivial, we can do that, but if it's a big data frame, that's going to slow everything down. But now I've split it, and I'm doing little small QR decompositions, which you can do. And in fact, if I have 5 cores on this, it's not going to take any longer than if I did the whole log in one go, because it just splits it up. So I split this into my QR decomposition. So easy enough, here's my code. Basically, I'm just using mutate with a map. I grab each of my x's, so each of my x's in here. So I go to each nested data frame. It will perform QR, and it will grab the Q, and it will perform the QR and grab the R. Not the cleanest code, because if you notice I'm doing the QR twice. I need to improve this code, but it was just for ease of understanding. Ideally, what I should do is take it and spit out 2, and then just map them back. But to be honest, if you're honestly doing map reduce, you wouldn't do it this way. In the last workshop, we'll show you how to do it using Sparkly R. So now I've got my 5 lots of Q1s and R1s. Now it starts getting funky. So there's my first Q1 and my first R1. So what I'm going to do is I'm going to grab all the R's. I'm going to create this new thing called R1, where I take all the R's and put them back together in a matrix. So that's what that's doing there. I'm doing a call. I'm saying what I want to do is an R bind, and the arguments are going to be all my R1s. So you can see what that's done is it's produced this new R1, which is a 10 by 2. So it took all of my 5, which were the upper triangles, upper triangular matrices, and it just bound them all together. So now I'm going to do another QR decomp of that. Now you say, well, wait a minute, why did you bother? Like, you've got this big matrix of QR, but notice the original one, I'd be doing a QR of 50 by 2. Now this one is just a QR of 10 by 2. So by doing that map and then bringing it together, I've reduced the size of the thing I've got to do the QR. And by balancing the number of modules, you can actually reduce this speed, reduce the computation down. So here's me doing that. So I do QR, and then I grab the Q2 and the R2. So I've got this Q2 and R2. Now I take Q2 and split it again into n blocks. So I've got another map stage. So we know how to do that already. So here's me doing the splitting. And here's me showing that the first one is that first 2 by 2. And now I calculate a Q3. So I take for each of those blocks, the first one I created of my Qs, the second one I created of my Qs, I put them together and create a new thing called Q3. Nice and easy, I'm going to use map 2. So map 2, we've done map, which will take a list and return a list. Map 2 will take 2 lists at the same time and perform an action on the first 2 elements of each list, and then the second 2 elements of each list, and then the third 2 elements of each list. So this is taking the first element of Q1 and the first element of Q2 and just multiplying them. And returns as Q3. Then it goes to the next two elements. And finally, we calculate a VI. So this is our reduced step, where I take my Q1Q to the third one, I transpose it and multiply it by the appropriate data. Easy enough. And then finally, I add them all together. So I'm pulling out that structure, like we said before. You could think about a nest to do this, but I do it with a reduce. So I'm adding them at the same time as taking them out. And then finally, you actually do this calculation. So it's really, really quite complicated. I do have the maths that goes with it, but I'm not going to go through the maths that shows this actually does it.
Did you figure it out when you were in your bike?
No, I figured this out
When you read a book?
I absolutely figured this out by using my secondary brain, which is Gary. Because it was just too many steps, and then he went away. I saw him on Thursday night, and I explained what I did, and I gave him the slides and said, I can't quite understand why it works. And he gave me a 5-page result the next day, the next morning. They explain exactly how it works. It's not that bad. It's actually quite nice. You're very welcome to look at it, but obviously I'm not going to go into the details.
It will not make a wonderful exam question.
No, it wouldn't. But the key idea here, and notice first of all the intersection and speed of good, is that this is possible. There is certain problems, even something like this where you have, this single matrix, you can split it. If you split it in the right way, and then do your map, and then do your reduce, you can actually reduce your computation. I would highly recommend that this is the sort of stuff you do not code yourself. Even with a lot of, knowing my map functions and doing this bit by bit, to write that code took me a good hour and a half. And I would never ever use that code because it's rubbish. What the idea is that there is algorithms out there that will let you take your problem, your statistical problem, and split it into multiple things in map, send that map off, let it do stuff, reduce, and get your answer back. Now, the way you do that is MapReduce was then an open source called Hadoop, and there's also a version called Spark. There's actually, by RStudio, a really nice package called Sparkly R. So Spark, L-Y, as in sparkly, and then R at the end, which does Spark R. There's also Spark R as well. Sparkly R, once you set up your system to use it, will do this automatically in the background. You don't have to do all these calculations. You just have ML for machine learning _ linear regression. And it will do all your map reduce automatically. There's random forest, the whole lot. So our last workshop, if we can get it to work, which is highly unlikely, would involve you all spinning up your own little Amazon cloud server, getting that to work, and then once you've got your machine, I will actually have an example of using Sparkly R, so you can see what you want to do. If you want to have a go in the meantime, go to the search Spark R or Sparkly R. There's tutorials. Key things, you have to install Spark to get it to work. Spark needs Java, and R can't always see Java. So the machines I've got set up for you, I've actually made a package image, so it's all ready to go. So it should be easier. At some point over the next couple of weeks before the workshop, you need to log into a website I'll send you called ronin.ura.cloud, and make sure that I've given you enough permissions you can see the Advanced Data Science project. Don't mess around at that point though. I will find out you're messing around and I will charge you, because we've only got a certain amount of money put aside, because using Amazon Cloud Service costs money. But if you can log on and make sure you can log on and you can see that, that's good. And then in the workshop, we'll actually spin up a machine each and have a go at doing some advanced stuff. That is it. Any questions on MapReduce? It's good. It's the next thing you need to learn. I'm not going into a lot of detail, But if you're going to start using real big data, you need to understand the basic concepts of MapReduce. It's not hard. Take your problem, break it up, parallelize it. Cool. Any questions? No. I will see you on Wednesday. Don't forget, we'll have a workshop on a method you need to bring laptops. Thank you very much. If you want that code, go to the thing, have a look at it, have a play, see how you go.